Right now, without thinking about it, you are using the most common thing in the universe. It's moving through every nerve in your body. It's holding together every atom you are made of. It's streaming into your eyes at this very moment as the light that lets you read these words. We call it energy. You've heard the word your whole life. You've paid for it, measured it in the units on an electricity bill, and learned a tidy little definition of it in school. And yet, when physicists went looking for what energy actually is, not what it does, but what it's made of at the very bottom of reality, the answer they found quietly took apart the picture they had been using for 300 years. It turned out that energy is not a substance. It is not a fluid, not a stuff, not some invisible material that pours into things and fills them up. It is something far stranger than that, older than matter, woven so deeply into the structure of the universe that, in order to explain it at all, physicists first had to rethink what a thing even is. Tonight, we're going to follow that single question all the way down. We're going to start with a burning candle and end at the edge of what human beings currently understand, in the space between the smallest particles and the largest structures in the cosmos. And by the end of this, you'll understand why the most ordinary thing in the world, the thing behind every heartbeat, every sunrise, every thought you've ever had, is also one of the deepest and most beautiful mysteries in all of physics. The honest answer to the question, what is energy made of, is not the one most people expect, but it might be the most remarkable answer science has ever arrived at. If you find these kinds of questions as quietly fascinating as we do, the slow, patient work of understanding how the universe is actually put together, take a moment to like this video or subscribe to the channel. It's a small thing, but it helps these journeys reach more curious minds who like to look up and wonder. And now, let's begin. Let's begin where you began, with what you were taught. Energy is the ability to do work. That's the definition most of us carried out of a school classroom, and it isn't wrong. But it's about as satisfying as describing music as vibrations in the air. Technically true, completely useless if what you actually want is to understand the thing you're holding. So set the textbook aside for a moment and imagine something simple instead. Imagine you're holding a lit match to the wick of a candle in a quiet room. Watch what happens. The wick catches, a small flame lifts and steadies. Light spreads outward and softens the shadows on the walls. The air just above the flame begins to shimmer. If you hold your hand near it, your skin grows warm, and slowly, over the next hour, the candle itself grows shorter, the wax retreating downward as if it were quietly disappearing. Every one of those things, the light, the warmth, the shimmer, the shrinking wax, is the same event. All of it is energy changing from one form into another. And here is the strange part. You have almost certainly watched a candle burn at some point in your life and thought nothing of it. It's one of the most ordinary sights there is, but you were watching something genuinely profound happen, dressed up as something completely mundane. You were watching the universe move a fixed quantity of something from one hiding place to another, without ever creating or destroying a particle of it. The candle was teaching you a law that took humanity centuries to notice. To see how we noticed it, we have to go back a long way, before quantum physics, before atoms were confirmed to exist, back to a time when the very idea that energy was a single, countable thing was brand new and slightly controversial. The first serious attempt to pin energy down as a real physical quantity came in the 17th century, from a German mathematician named Gottfried Wilhelm Leibniz. You may know his name from a different fight entirely. He invented calculus at around the same time as Isaac Newton, independently, and the two of them spent years in a bitter argument over who got there first. But Leibniz was also watching the way objects move and collide, and he noticed something that wouldn't let him go. When things crash into one another, roll, bounce, and settle, a certain quantity seems to survive the whole messy process unchanged. He called it vis viva, living force. In modern terms, it was very close to what we now call kinetic energy, the mass of an object multiplied by the square of its speed. That little detail, the square of the speed, is worth pausing on because it's easy to skate past, and it turns out to matter enormously. It means that if you double how fast something is moving, you don't double its energy of motion, you quadruple it. A car traveling at 60 miles an hour doesn't carry twice the energy of one traveling at 30. It carries 4 times as much, which is exactly why a crash at high speed is so much more violent than our intuition expects. Leibniz didn't know why the relationship should be squared rather than simple. Nobody did. As it happens, that squared term is written into the geometry of space and time itself. But the human race wouldn't understand that for another 200 years. For now, it was just a curious pattern in the arithmetic of collisions. In the decades after Leibniz, scientists began doing something that sounds simple but was quietly revolutionary. They started making a list. They catalogued all the different phenomena that seemed to belong to this same mysterious family: heat, motion, electricity, magnetism, light. On the surface, these things could not look more different from one another. The warmth of a fire has nothing obvious in common with a bolt of lightning, and neither seems related to the beam of a lantern. And yet, experiment after experiment kept revealing the same uncomfortable, wonderful fact. These things could be turned into each other. Heat could be made to produce motion, as in a steam engine. Motion could be made to produce electricity, as in a generator. Electricity could be made to produce light. Each one could be converted into the next, as if they were all different currencies for the same underlying wealth. And here is the part that made careful people sit up. Through every one of these conversions, the total amount seemed to stay exactly the same. Nothing leaked away. Nothing appeared from nowhere. Whatever was going on beneath the surface, the universe appeared to be keeping a perfectly balanced ledger. The person who nailed this down with real precision was an unlikely figure, a British brewer named James Prescott Joule, working in the 1840s, partly in his spare time, as a serious amateur physicist. Joule wanted to know exactly how much motion turned into how much heat. So he built a beautifully simple machine. He hung weights from strings and let them fall. As they fell, they turned a set of paddles submerged in a tub of water. The paddles churned the water, and Joule measured, with obsessive care, the tiny rise in the water's temperature caused by all that churning. Think about how small that effect is. You could stir a glass of water with a spoon all day and never feel it get warmer. Joule had to measure temperature changes so slight that most people wouldn't believe they were real. But he found something extraordinary. The relationship was fixed, exact. A certain amount of falling motion always produced the same certain amount of heat, every single time. The work done by the falling weights didn't mostly become heat, with a little lost along the way. It completely became heat, in a perfectly reliable ratio. One measured unit of mechanical work produced one matching unit of heat, not roughly, not approximately, but exactly, as far as his instruments could tell. By the middle of the 19th century, all of this had hardened into one of the most important principles in the whole of science. We call it the conservation of energy. Energy cannot be created, and it cannot be destroyed. It can only be moved and changed from one form into another. The candle you imagined earlier is a small, quiet demonstration of that law. The energy locked inside the wax doesn't vanish as it burns. It simply changes costume, into light, into heat, into the warmed and rising air, and the books always balance. What made this discovery so haunting was not that it was strange, but that it hinted at something hidden underneath the world. There was a quantity that the universe seemed to be tracking. Whatever chaos was unfolding on the surface, fires burning, wheels turning, storms breaking, hearts beating, the total amount of this one quantity never changed. The universe was conserving something with perfect, tireless accuracy. And the deep, uncomfortable question that came with that realization was simple to ask and impossible, at the time, to answer. Why? Why should the universe care? What was this thing it was so carefully counting? That question sat mostly unanswered for a very long time, buried under the roaring practical success of the age. Because here's the thing, you don't actually need to know what energy is in order to use it. Engineers could calculate energy transformations with total confidence without ever understanding what energy fundamentally was. The mathematics worked. That was enough. Steam engines powered the Industrial Revolution. Factories multiplied. Railways stitched continents together. Cities swelled with light and machinery. Amid all that thundering progress, the question of what energy actually is, deep down, at the bottom, seemed almost like a philosopher's daydream. Interesting, perhaps, but irrelevant to the serious business of building the modern world. And then, in the first years of the 20th century, physics changed, not once, but twice, in quick succession, and neither change was one that anybody was expecting. The first of those two changes grew out of a problem that had been quietly nagging at physicists since the 1890s. It had a wonderfully dramatic name, the ultraviolet catastrophe, and to understand it, you first need to notice something you've seen with your own eyes many times. When you heat something up enough, it starts to glow. Picture a blacksmith's forge, or the coil of an electric stove as you turn it on. The metal begins in ordinary darkness. Then, as it grows hotter, it flushes a deep red. Hotter still, and it brightens to orange. Push the temperature higher, and it climbs to a fierce yellow-white. The color of the glow is telling you the temperature, and this isn't limited to hot metal. Every object, everywhere, at any temperature above absolute zero, is quietly radiating energy in the form of light. Most of the time that light is at wavelengths your eyes can't see, but it's always there. You are doing it right now. Your body is gently glowing in infrared, a warmth you shed into the room around you every second. The hotter the object, the more it radiates, and the shorter the wavelengths it favors. This is the reason the stars come in different colors. A cool star burns red, a hotter star shines white. The very hottest blaze blue-white. Our own sun sits somewhere in the middle, radiating most strongly in the yellow-green part of the spectrum. So the glow of a heated thing is not a random side effect. It follows precise rules, and physicists in the late 1800s thought they understood those rules rather well. They had equations that described how a warm object should spread its radiated energy across different frequencies of light. And for a while, those equations behaved. At low frequencies, the long, lazy wavelengths down toward the infrared, the math agreed beautifully with what experiments measured. But when physicists pushed the same trusted equations toward high frequencies, toward the ultraviolet end of the spectrum and beyond, something went horribly wrong. Not slightly wrong, not off by a little, catastrophically, absurdly wrong. The equations predicted that a warm object should pour out an infinite amount of energy at high frequencies. Not a large amount, not an enormous amount, infinite. And if that were true, the consequences would be lethal in the most ridiculous way imaginable. Sitting near a warm stove, or standing next to another warm human being for that matter, should bathe you in an infinite flood of ultraviolet radiation and vaporize you instantly. Every warm thing in the universe would be a death ray. Now, obviously, that is not what happens. People warmed themselves by stoves every single day and lived to tell about it. The world was plainly full of warm objects that were not incinerating everything around them. And yet the mathematics of classical physics, the very best physics of the age, insisted, with a straight face, that they should. This was the ultraviolet catastrophe, and the reason it deserved such a heavy name is that nobody could fix it. Every attempt to patch the equations broke something else that was known to be true. The problem sat there like a crack in a wall that kept spreading no matter how you filled it. In the year 1900, a careful, conservative German physicist named Max Planck found a way to make the crack close. But the fix cost him something. To make it work, he had to slip an idea into the mathematics that he himself found deeply, personally uncomfortable, an idea so odd that he spent much of the rest of his life trying to explain it away. Here is the idea. Planck proposed that energy is not smooth. It does not flow in a continuous, unbroken stream the way we naturally assume. Instead, it comes in tiny, separate, indivisible packets, discrete little chunks, each one a fixed minimum size. He called these packets quanta, from the Latin word for how much, and this single word would go on to name an entire new physics. Let me give you the everyday picture Planck was fighting against, because the contrast is the whole point. Classical physics treated energy like water. If energy is like water, you can have any amount you like. You can pour exactly 1 liter, or 2, or 1 3/8, or any fraction in between, smoothly, with no gaps. There's no smallest possible sip. Planck was suggesting that energy is not like water at all. Energy, he said, is more like coins. You can have 1 coin, or 2, or 100, but you cannot have 1.5 coins. There is a smallest unit, and everything comes in whole multiples of it. You get the whole packet, or you get nothing. And here was the clever heart of his solution. Planck said the size of each packet depends on the frequency of the light involved. The higher the frequency, the larger the minimum packet you'd need to make even one of them. So at ordinary temperatures, the very high frequency modes of radiation simply couldn't get started because there wasn't enough energy lying around to afford even a single one of their expensive packets. They were, in effect, frozen out, priced out of existence. And the moment you build that rule into the math, the infinite runaway at high frequencies simply vanishes. The equation heals itself. The catastrophe disappears. Planck had done something enormous, and he had done it almost by accident, while trying to solve what looked like a narrow, technical problem about glowing objects. He was not trying to overthrow physics. He was a deeply traditional man who trusted the classical picture of the world. He was simply trying to get one stubborn equation to stop predicting nonsense. And he succeeded, at the price of proposing something that made the smooth, continuous, classical picture of energy impossible to keep. Because if Planck was right, then energy, at its most fundamental level, comes in indivisible lumps. There is a smallest possible amount of energy that can be involved in any given process. You cannot have half of one of these packets. You cannot have a third. The universe, at bottom, does not do smooth. It does grainy. He captured the whole idea in an equation so short you could write it on a fingernail. The energy of a single packet equals a certain constant, now called Planck's constant, in his honor, multiplied by the frequency of the light. And that constant is a staggeringly, almost unimaginably tiny number. Written out, it's roughly a decimal point followed by 33 zeros and then a 6. It is so small that in ordinary life you could never, ever notice the graininess it describes. When you flip on a lamp, the energy really is arriving in separate packets, but the packets are so fantastically small, millions upon billions of times smaller than anything your senses could register, that the light appears perfectly smooth and continuous. the way a beach looks smooth from a distance, even though it's made of countless separate grains of sand. Walk close enough, though, and the grains are all there is. And at the scale of atoms and the particles inside them, we are standing right down on the sand. Down there, the graininess of energy isn't a technicality, it's everything. Planck himself was never comfortable with what he'd done. He suspected he might have found only a mathematical trick, a clever bookkeeping device that made the numbers come out right without necessarily describing how nature truly worked underneath. He spent years afterward trying to find some other way to solve the glowing object problem, some route that didn't require these strange packets. He never found one. He had opened a door, and he wasn't at all sure he wanted to walk through it. It would take a younger, bolder mind to step across the threshold and refuse to come back. That mind belonged to a 26-year-old patent clerk in Bern, Switzerland, named Albert Einstein. In 1905, Einstein was not yet the icon whose face would one day hang on classroom walls. He was a young man with a steady day job examining patent applications, doing physics in the evenings and the margins of his working hours because he couldn't stop. And in that one year, a year physicists still speak of with something close to reverence, he published 4 papers, any single one of which would have been the achievement of a lifetime. One of them explained the jittery, restless dance of tiny particles suspended in a fluid, and in doing so, gave some of the strongest evidence yet that atoms were real. Another laid out the special theory of relativity. A third, almost as an afterthought, derived the most famous equation in the world. Energy equals mass times the speed of light squared. And we'll return to that one later, because it hides a secret about energy that took decades to fully appreciate. But the paper that matters most for our story right now was the 4th. It tackled a small, stubborn puzzle that had been sitting in physics since the 1880s, called the photoelectric effect. The setup is this: shine light on a piece of metal, and under the right conditions, the metal will spit out electrons. That much was understood. Light carries energy. Energy can knock electrons loose. No mystery there. The mystery was in the details, and the details refused to behave. Classical physics, treating light as a smooth wave, made a very reasonable prediction. A brighter light carries more energy, so a brighter light should knock electrons out harder, giving each one a bigger kick. And if you shone even a dim light for long enough, the energy should gradually accumulate, like water slowly filling a bucket, until eventually there was enough to send electrons flying. Both of these predictions felt obvious. Both of them were wrong. What experiments actually showed was baffling. The energy of each electron that came flying out depended not on the brightness of the light at all, but entirely on its color, that is, its frequency. A dim violet light would eject electrons with more energy than an intensely bright red light, and below a certain frequency, red light produced no electrons whatsoever, no matter how blindingly bright you made it. You could shine that red light on the metal for an hour, for a year, for a lifetime. Not one electron would emerge. Turning up the brightness of a light that was too low in frequency just gave you more of nothing. Classical wave theory had no explanation for this. None. It was a wall. Einstein walked straight through it by taking Planck's uncomfortable idea and pushing it much further than Planck had dared. Planck had suggested that energy comes in packets when it is emitted or absorbed. Einstein proposed something bolder, that light itself, as it travels through empty space, is made of packets. Not a smooth wave at all, but a stream of discrete particles, each one a tiny bundle of electromagnetic energy, each carrying an amount equal to Planck's constant times the frequency. He called them light quanta, we call them photons. And suddenly the photoelectric effect made perfect, simple sense. Picture it not as a wave washing over a beach of electrons, but as a hail of individual pebbles. One photon strikes one electron. The energy that single photon carries depends only on its frequency. High frequency, high energy. Low frequency, low energy. If a photon carries enough energy to break the electron free from the metal's grip, the electron escapes, and it escapes with whatever energy was left over. If the photon doesn't carry enough, as with that low-frequency red light, then nothing happens. The electron absorbs the little bundle, gets a gentle nudge, and stays exactly where it is. Making the light brighter just means throwing more pebbles. It gives you more chances, so more electrons come out. But it does nothing to change how hard any single electron is hit, because that depends only on the individual photon that strikes it. And crucially, you can't save up. There's no way to store half a photon's worth of energy and wait for another half to arrive. Each collision is complete in itself, an all-or-nothing transaction. It was a clean and elegant answer. It was also deeply disturbing, and Einstein knew it. Because light, everyone knew, was a wave. This wasn't a hunch. It had been proven, decisively, more than a century earlier. Back in 1801, a physician and polymath named Thomas Young had done one of the most beautiful experiments in the history of science. He let light pass through two narrow, closely spaced slits and fall onto a screen behind them. If light were made of simple particles traveling in straight lines, you'd expect two bright stripes on the screen, one behind each slit. That is not what appeared. Instead, there was a whole series of alternating bright and dark bands spread across the screen. This is the signature of waves. When water waves pass through two openings, they spread out and overlap on the far side. And where two crests meet, they reinforce each other. And where a crest meets a trough, they cancel out, leaving a rippling pattern of reinforcement and cancellation. Young's bands were exactly that pattern, made of light. It was as close to a definitive proof as science ever gets. Light was a wave. And then, in the 1860s, the Scottish physicist James Clerk Maxwell had gone further still, writing down a set of equations of breathtaking elegance that described light as a self-sustaining wave of electric and magnetic fields, rippling through space at, well, the speed of light. Maxwell's equations were one of the crowning achievements of classical physics. They didn't just suggest light was a wave, they explained what kind of wave it was, and they had been confirmed again and again. So the wave nature of light was not speculation. It was bedrock, and now here was Einstein, calmly insisting that light was also a particle. Not sometimes one and sometimes the other, depending on the day, but genuinely both at once, showing you one face or the other, depending only on how you chose to look at it. Pass light through two slits, and it behaves as a wave, interfering with itself. Fire it at a metal plate, and it behaves as a stream of particles, striking electrons one by one. This was the opening of one of the strangest and most productive ideas in all of physics, wave-particle duality. The notion that the deepest constituents of reality are neither purely waves nor purely particles, but something for which our ordinary human categories, shaped as they were by pebbles and ponds and everyday objects, simply have no word. Something genuinely new that would demand an entirely new framework to describe. And it did not stop with light. In the early 1920s, a French graduate student named Louis de Broglie, an aristocrat who had come to physics somewhat late by way of history, asked a question so simple and so bold that his own thesis committee didn't quite know what to make of it. If waves can behave like particles, he wondered, then why shouldn't particles behave like waves? Why should the strange duality run in only one direction? In his doctoral thesis, de Broglie proposed that every particle with mass, every electron, every atom, in principle every object, has a wavelength associated with it. And he wrote down what that wavelength should be. Planck's constant divided by the particle's momentum. The faster and heavier the particle, the shorter its wavelength. For anything large, a baseball, a person, a planet, the wavelength is so absurdly tiny that it's utterly undetectable, which is exactly why we never notice ourselves behaving like waves as we walk down the street. But for something as light as an electron, the wavelength becomes large enough to matter. De Broglie's committee stared at this and hesitated. It was gorgeous mathematics, but what could it possibly mean? An electron was a tiny ball of charge. Everyone knew that. So they did something sensible. They sent a copy of the thesis to Einstein and asked what he thought. Einstein wrote back that it looked like it might well be right. That was enough. They passed him, and a few years later, de Broglie was awarded the Nobel Prize because the experiments came in and he had been exactly right. At Bell Labs in the United States, two researchers named Clinton Davison and Lester Germer fired electrons at a crystal and found that the electrons came off in a pattern of alternating bright and dark bands, the very same interference pattern you get from waves. Across the ocean in Britain, George Thomson found the same thing, independently. Electrons, those supposedly simple little balls of charge, with definite masses, definite charges, that curved in predictable arcs through magnetic fields, were interfering with themselves, spreading out and overlapping and canceling, doing something that only a wave can do. There is no way to fake an interference pattern with ordinary particles. The electrons were behaving as waves, with precisely the wavelength de Broglie's formula had predicted. So now the strangeness had spread from light to matter itself. The same electron that was clearly a particle was also, unmistakably, a wave. Both descriptions were true at the same time, and the question of how on earth to reconcile them, how to build a single, consistent picture of a nature that refused to be either one thing or the other, drove physics into perhaps the most intense decade of theoretical work the field had ever seen. The greatest minds of the era threw themselves at it, arguing at conferences, demolishing one another's proposals in a flurry of papers, all wrestling with the same impossible-seeming problem. And the answer they eventually arrived at would not just describe atoms, it would completely rewrite what physicists meant by the word energy. The resolution arrived in the late 1920s, and it came with a new name for what physicists were doing: quantum mechanics. At its heart sat a radical new picture of what energy is and how it relates to the world. But to get there, we have to meet the equation that started it. In 1926, working in Zurich, a physicist named Erwin Schrödinger wrote down an equation describing how a quantum system changes over time. It's often called simply the Schrödinger equation, and it is to quantum mechanics roughly what Newton's laws are to ordinary mechanics, the master rule everything else flows from. But it describes something profoundly unlike anything in Newton's world. Newton's equations tell you where a thing is and where it's going. Throw a stone, and Newton will tell you its exact path, this height at this instant, that speed at that moment, landing precisely there. Schrödinger's equation does no such thing. It does not tell you where a particle is. It does not give you a trajectory. Instead, it describes the evolution of a strange mathematical object called the wave function, a kind of invisible field that spreads through space and assigns a value to every single point. The wave function holds all the information it is possible to have about a system, and Schrödinger's equation tells you, precisely and reliably, how that wave function ripples and shifts and evolves from one moment to the next. Here's where it gets genuinely unsettling. To find out where the particle actually is, you take the wave function's value at a point and, roughly speaking, square it. What you get is not a location, it's a probability, the chance of finding the particle there if you go looking. Before you measure it, the particle does not have a single definite position at all. It has a spread of possible positions, each with its own probability, all somehow coexisting. Only in the act of measurement does that spread suddenly collapse to a single, definite answer. And this is the part that troubled even the people who built the theory. When the particle finally shows up in one place rather than another, that outcome is genuinely random. Not random because we were too ignorant to predict it. Not random because some hidden detail was out of our reach. Random because, before the measurement, there simply was no fact of the matter. The universe had not yet decided. This sounds like philosophy, like a word game, but it is not. It is physics, and it has been demonstrated in thousands of experiments. In the 1960s, a physicist named John Bell worked out a precise mathematical test that could tell the difference between a genuinely undecided universe and one that was merely hiding its answers from us. And in the early 1980s, Alan Aspect and his colleagues carried out that test in the laboratory. The verdict was clear, and has only grown clearer since. The universe really is indeterminate at its foundations. It really does deal in probabilities. There is no secret script. Now hold that picture in mind, because here is what it does to the idea of energy. In quantum mechanics, energy is no longer just a number a particle carries around, like its weight in a pocket. Energy becomes something more abstract. It corresponds to a mathematical operation you perform on the wave function. And when you actually measure the energy of a confined quantum system, you don't get to find just any value you please. The wave function collapses into one of a specific, limited menu of allowed states, and only the particular energies belonging to those states are ever available. Not a smooth, continuous range, a discrete set, a fixed list of permitted answers with forbidden gaps in between. This is the moment where Planck's graininess stops being a clever trick and reveals itself as something woven into the deep structure of reality. Energy comes in steps, because the wave equation, when you solve it for a system that's boxed in, simply has no solutions except at certain special values. And there's a wonderful everyday analogy for this, one you can hear. Think of a guitar string, stretched tight and pinned down at both ends. Pluck it, and it doesn't produce every possible pitch. It produces one clear note, its fundamental, along with a specific ladder of higher tones above it, the harmonics. It cannot sound a pitch that falls between those notes. Try as you might, you can't make a fixed string hum at some arbitrary in-between frequency, because such a vibration simply doesn't fit. The ends are held still, and only certain waves are shaped right to sit neatly between them, with the ends staying put. Every other frequency is impossible, not forbidden by some rule enforced from outside, but impossible in the way that a jigsaw piece from the wrong puzzle just doesn't fit the whole. The energy levels of a quantum system work in exactly the same way. Only certain values are genuine solutions to the wave equation for that system. The others aren't blocked or banned. They just aren't part of the vocabulary. They don't exist as valid answers to the question the system is asking. The universe isn't standing guard, prohibiting those energies. They're simply not solutions, like notes that no string of that length can ever sound. Let me make all of this concrete with the simplest system in the cosmos. A single hydrogen atom, one proton and one electron. Nothing could be more basic, and it turns out to be a perfect little laboratory for everything we've been building toward. Classical physics had a genuine crisis with the hydrogen atom, and it's worth feeling the full weight of it. In the classical picture, the electron orbits the proton the way a planet orbits the sun, and it should be able to do so at any distance, with any energy. The closer the orbit, the lower the energy, in a smooth, continuous range. But classical physics also insisted on something else, that any electric charge, which is accelerating, must radiate energy away as light. And an electron swinging around in a circle is accelerating every instant because it's constantly changing direction. So the classical electron should be endlessly bleeding energy into radiation, spiraling inward, winding down like water circling a drain. And when you do the arithmetic, the collapse is not slow. A classical hydrogen atom should spiral into its own nucleus and cease to exist in about 10 billionths of a second. Not 10,000 years, not 10 years, 10 billionths of 1 second. Sit with that for a moment, because you are a walking contradiction of it. You are built, in large part, from hydrogen, oxygen, carbon, nitrogen, atoms with electrons that, according to classical physics, should have collapsed almost instantly at the dawn of time. The atoms in your body have held themselves together, stably, for billions of years. Every classical calculation says that should be impossible. And yet here you are. Quantum mechanics explains why you're here. The electron in a hydrogen atom is not orbiting in any ordinary sense. It exists as a wave function, spread out in a cloud around the proton, and that wave function has stable solutions only at certain specific energies. There's the ground state, the lowest rung on the ladder, where the electron is most likely to be found at a distance of about 53 trillionths of a meter from the proton. Above it sits the first excited state, with a little more energy and a slightly larger cloud. Above that, the second excited state, larger still. And so on, up a ladder of allowed energies. The electron cannot exist between these rungs. There is no in-between. It can leap from one rung to another, but only by absorbing or releasing a photon carrying exactly the energy difference between them. Exactly. This is the crucial word. If you shine light on a hydrogen atom at almost the right frequency, close but not perfect, nothing happens. The photon sails straight through, ignored, as if the atom weren't there. Only a photon whose energy precisely matches the gap between two rungs will be absorbed. And when an electron falls from a higher rung to a lower one, it emits a photon of exactly that same precise energy, no more and no less. This is why every chemical element has what we call spectral lines, sharp, specific colors it absorbs and emits, and no others. Not a smeared rainbow, but a set of clean, narrow lines, like a barcode. Each element has its own unique barcode, a fingerprint written in light, set entirely by the ladder of allowed energies inside its atoms. And here is the part that ought to give you a small shiver. That fingerprint is identical for every atom of that element, anywhere. The hydrogen in the glass of water beside you, the hydrogen fusing in the core of the sun, the hydrogen in a galaxy so distant that its light has been traveling toward us for 12 billion years, since long before the Earth existed. Same rungs, same spacing, same barcode, exactly. When we read the light of that ancient, unreachable galaxy, we find the very same energy ladder we measure in a laboratory here on Earth. The laws of quantum mechanics do not vary from place to place. They don't depend on an atom's history, or the century, or the corner of the universe it happens to occupy. Every hydrogen atom in all of creation carries the same allowed energies, set by the same handful of fundamental constants. And one of those constants is Planck's constant, the very same fantastically tiny number Planck reluctantly introduced in 1900 to tame the glow of a heated object. It turns up again and again everywhere you look in the quantum world, in the spectral lines of atoms, in the way atoms bond into molecules, in the structure of atomic nuclei, in the strange attraction between two mirrors in a vacuum that we'll come to shortly. Planck's constant is the fundamental unit of the graininess of nature, and every discrete energy rung in every atom, in every star, in every galaxy is spaced out in multiples of that single unimaginably small number. It is stitched into the fabric of everything. But even now, having come this far, we still haven't answered the real question. We've learned that energy comes in packets, and we've learned why, but we haven't yet asked what energy is. What exactly is this thing that's being handed around in packets? Where does it live? What is it made of? And to answer that, we have to let go of the last comfortable idea we've been quietly holding on to. The comfortable idea is this, that energy is always attached to something. In the classical picture, energy was never a thing in itself. It was always a property of some object, a description of the state something was in. A rolling boulder has kinetic energy because it's moving. A drawn bow has stored energy because it's bent. A warm cup of tea has thermal energy because its molecules are jostling about. A charged battery holds energy because of how its charges are arranged. In every case, the energy belonged to a thing. It was an adjective, not a noun. Ask where is the energy, and the answer was always in the boulder, in the bow, in the tea. Energy was a way of describing objects. It was never the object itself. Quantum mechanics had already begun to loosen this picture, but the framework that came next, the one that represents our deepest current understanding, dissolved it entirely and replaced it with something so different that even physicists who have worked with it for decades sometimes struggle to hold it steady in their minds. That framework is called quantum field theory, and to reach it, we have to follow a thread that begins with a puzzle, an act of pure reasoning, and the prediction of a kind of matter nobody had ever seen. Quantum field theory grew out of the marriage of two of the great theories of the 20th century, quantum mechanics and special relativity. It became necessary the moment physicists tried to describe particles moving at speeds close to the speed of light. Schrödinger's original equation, for all its power, had a flaw. It treated time and space differently from one another, and Einstein's relativity had shown that you're not allowed to do that. In relativity, space and time are woven together into a single fabric. You cannot pull them apart and handle them separately. So physicists needed a new equation, one that honored both quantum mechanics and relativity at the same time. In 1928, an extraordinarily quiet and precise English physicist named Paul Dirac found it. The Dirac equation described the electron correctly even at nearly the speed of light, and it was a triumph, mathematically beautiful and physically accurate. But it came with a bizarre and unwelcome feature. The equation had solutions describing electrons with negative energy, and that seemed like nonsense. What could an electron with negative energy even mean? Worse, if such states existed, ordinary electrons should tumble down into them endlessly, releasing energy without limit, and the stable matter of the world should be impossible. Dirac's way out was one of the strangest and most creative ideas in the history of physics. He proposed that all of those negative energy states were already occupied, every single one of them, everywhere, filled with electrons, forming an invisible, uniform sea that pervades all of space. We call it the Dirac Sea. Because it was completely full and completely uniform, we wouldn't notice it. It would be like the pressure of the air, always present, never felt. But then Dirac asked, what if you punched a hole in that sea? What if one of those negative energy electrons were kicked out, leaving a gap? That gap, he realized, would behave like a real particle, with the same mass as an electron, but the opposite electric charge, a positive electron. No such thing had ever been observed. Dirac first wondered, tentatively, whether the gaps might be protons, but the numbers refused to cooperate, because a proton is nearly 2,000 times heavier than an electron. So the prediction stood there, naked and untested. Somewhere out there, waiting to be found, was a mirror image twin of the electron, identical in every way except that it carried the opposite charge. And in 1932, a physicist named Carl Anderson studying the faint tracks left by cosmic rays streaking through a device called a cloud chamber, found it. A particle exactly like the electron, but positively charged. We call it the positron. This was the very first piece of antimatter ever discovered, and it had been conjured, in advance, out of nothing but the demand that quantum mechanics and relativity be made to agree. That is the kind of thing that makes physicists believe they are onto something real. The Dirac Sea, with its awkward infinite ocean of hidden electrons, was eventually replaced by a cleaner and deeper framework that could handle all of this without the strange imagery. And that framework was quantum field theory. Its central idea changed everything about how to think of particles, of energy, and of what the universe is fundamentally made of. So let's build that idea slowly, because it's the turning point of our whole story. Start with the word field, and forget physics for a second. A field, in the plain sense, is just a quantity that has a value at every point in a region. The temperature in a room is a field. Every point in the room has some temperature, and if you could paint them all, you'd see a smooth map of warmth and coolness filling the space. The wind over a landscape is a field. At every point in the air, there's a direction and a speed. These are ordinary, familiar things. Now, physicists have long known that some of nature's most important actors are fields of this kind. The electromagnetic field is one. At every point in space, it has an electric and a magnetic value, and its ripples are what we call light. Quantum field theory takes this idea and does two astonishing things with it. First, it says that all of these fields are quantum. They don't sit at fixed, definite values. Like the wave functions we met earlier, they are uncertain, they fluctuate, they can only be described in terms of probabilities. And second, this is the crucial move. It says these fields fill all of space, not just where matter happens to be, everywhere, at every point in the universe, all the time. There is an electron field, and it has a value at every point in the cosmos. There is a field for the quarks that make up protons and neutrons, and it too spans all of space. There's a field for the photon, one for each of the other force-carrying particles, one for the Higgs. Every fundamental particle you have ever heard of is, in this picture, associated with a field that fills the entire universe at all times, simultaneously. Space is not an empty stage on which particles perform. Space is thick with fields, layered over one another, everywhere at once. And now comes the idea that reframes everything. In quantum field theory, particles are not the fundamental things, the fields are. A particle is nothing more than a localized excitation of its field, a place where the field has been disturbed, given a kick of energy, and set vibrating. Disturb the electron field in the right way, and that ripple of disturbance is what we call an electron. Disturb the electromagnetic field, and the ripple is a photon. Disturb the Higgs field, and you get a Higgs boson. Every particle in nature is a vibration in an underlying field that fills all of space. Here is the analogy that finally makes it land. Think of the ocean. A wave rolling across the surface of the sea is not a separate object sitting on top of the water, a thing you could scoop out and carry away in a bucket. The wave is the ocean, doing something. It's a pattern of movement in the water itself. Take away the ocean and there is no wave. There was never a wave thing to begin with, only water in motion. Quantum field theory says a particle is exactly like that. The electron is not a tiny ball floating in the electron field. The electron is the electron field, doing something. It's a ripple, a moving pattern of disturbance, in a field that was always there. Take away the field and there is no particle, because the particle was never a separate thing. It was the field, briefly, in a certain shape. And this, finally, reframes energy completely and answers the question we've been circling from the very beginning. In quantum field theory, energy is not a property that particles have. Energy is what particles are. When you pour energy into a quantum field, a particle appears. The energy takes the form of an excitation. When that particle is absorbed and vanishes, the energy flows back into the field. The particle and its energy are not two things linked together. They are one and the same event, seen from two angles. You cannot peel them apart. The particle is the energy. The energy is the particle, that rolling boulder from the classical picture, whose energy was merely a description of its motion. Down here, at the bottom, the description and the thing have become the same. Energy has stopped being an adjective. It has become the noun, after all. That single shift, from energy as a property of things to energy as the very stuff that things are made of, is one of the deepest changes in perspective in the whole history of science. And it leads directly to something that sounds, at first, completely impossible. The impossible-sounding thing is this. Even when a quantum field is in its very lowest possible energy state, when there are no particles in it, when nothing is happening, when it is as empty and quiet as it can possibly be, it still has energy. Genuine emptiness, as far as quantum mechanics is concerned, is not the absence of everything. It has a hum. This lowest, quietest state is called the quantum vacuum, and it is not nothing. It is the floor beneath which you cannot go, the state from which no more energy can be drained, and yet that floor is not at zero. Why should empty space refuse to be truly empty? The reason comes from one of the most famous ideas in all of physics, the Heisenberg uncertainty principle. You may have heard it stated in terms of a particle, that you can't simultaneously know both exactly where a particle is and exactly how it's moving. The more precisely you pin down one, the more the other blurs. But the principle is far more general than that. It applies to fields too. For a quantum field, it says you cannot simultaneously know both the exact value of the field at a point and exactly how fast that value is changing. Nail down one perfectly, and the other becomes completely undefined. And here's the beautiful trap this sets. Suppose the field really were perfectly still and perfectly zero everywhere, dead flat, not moving at all. Then you would know both its value, 0, and its rate of change, also 0, with perfect precision, at the same time. And that is exactly what the uncertainty principle forbids. So the field cannot hold perfectly still. It is forced, by the deepest logic of quantum mechanics, to tremble, to fluctuate endlessly around 0, never settling, never resting, not because anything is shaking it, not because there are hidden particles bouncing around inside it, but simply because perfect stillness is a kind of certainty that nature does not permit. It's worth being very clear about what this is not. This trembling is not a limitation of our instruments. It's not that our detectors are too clumsy, or that the act of looking disturbs what we're trying to see. That was an early, tempting misreading of the uncertainty principle, and it's wrong. The fluctuations are not about our ignorance. They are a real, physical feature of the quantum world, built into the mathematics, and, as we're about to see, measurable in the laboratory. We call them vacuum fluctuations, and they carry energy, the energy of empty space itself. There's a phrase you may have encountered for one way of thinking about all this: virtual particles. It's a slightly misleading name, so let me be careful with it. Virtual particles are not tiny things that almost exist, or particles that flicker into being and vanish before you can catch them, as they're sometimes loosely described. They are, more honestly, a mathematical bookkeeping tool, a way of calculating the effects of the fluctuations in the vacuum. When physicists work out how real particles push and pull on one another, using the diagrams and equations of quantum field theory, they find they must include contributions from these virtual particles to get the right answer. The virtual particles themselves can never be directly detected, but their effects are absolutely real and absolutely measurable. And nothing demonstrates that more cleanly than a beautiful and slightly eerie phenomenon called the Casimir effect. In 1948, a Dutch physicist named Hendrik Casimir, working at the Philips Research Laboratory in the Netherlands, was thinking hard about the quantum behavior of the electromagnetic field. And he made a strange prediction. Take two ordinary metal plates, flat, uncharged, electrically neutral, and place them extremely close together, facing one another, in a perfect vacuum. Casimir predicted that the two plates would feel a force pulling them together, not because of gravity, which at that scale is millions of times too feeble to matter, not because of any static electricity, since the plates carried no charge. The attraction, he said, would come from the quantum vacuum itself, from the empty space between the plates. Here's the picture. Remember that empty space is humming with vacuum fluctuations of the electromagnetic field, ripples of every possible wavelength, everywhere. But when you slide two metal plates very close together, you impose a constraint on the space between them. The electromagnetic field has to satisfy certain conditions at a metal surface, and the upshot is that only ripples with just the right wavelengths to fit neatly between the plates are allowed to exist in that narrow gap. Wavelengths that are too long simply can't fit. They're excluded. But outside the plates, in the open space beyond them, there's no such restriction. Out there, ripples of every wavelength continue to hum away as normal. So you end up with an imbalance. In the crowded open space outside, the full riot of vacuum fluctuations presses inward on the plates. In the restricted gap between them, only a thinned-out subset of fluctuations is allowed, pressing back. The outside pushes harder than the inside, and the result is a gentle but real force squeezing the two plates together, a force born entirely from the structure of empty space. For decades, this was a prediction on paper, a lovely idea at the edge of what could be tested. Then, in 1997, a physicist named Steve Lamoureux at Los Alamos National Laboratory measured it. He brought surfaces to within about a micrometer of each other, a thousandth of a millimeter, and detected the tiny Casimir force, and found it matched the prediction with real precision. Since then, it has been measured again and again in laboratories around the world with ever greater sensitivity and ever cleverer setups. The force changes when you change the spacing between the surfaces, just as the theory says it should. It changes when you use different materials or different shapes, flat surfaces, curved surfaces, patterned surfaces, superconducting surfaces. Every time, the measurement agrees with the quantum field theory prediction. Take a moment to feel the strangeness of what that means. Two plates, in a vacuum, in the dark, touching nothing, and they are drawn together by the energy of empty space. What the Casimir effect proves, cleanly and undeniably, is that the vacuum between those plates has less energy than the vacuum outside them. The geometry of a region of space affects the energy of the emptiness within it. Empty space has energy, it has structure, and that structure can be reshaped by the physical arrangement of matter around it. The vacuum is not nothing, it is a quantum field lying in its ground state, and that ground state hums with energy, and the shape of the space around it decides how much. And it's precisely here, having established beyond doubt that empty space carries energy, that our story runs headlong into what may be the single most embarrassing and profound problem in all of modern physics. Because think about what we've just established. If empty space has energy, then the universe should be brimming with it. Every cubic centimeter of vacuum, every region of nothing, everywhere across the entire cosmos should carry this ground state energy. So physicists did the natural thing. They tried to calculate how much. They added up the contributions of all the quantum fields in nature to the energy of the vacuum, summing over all the fluctuations of all the different types of fields, and the number they got per cubic meter of empty space was a 1 followed by something like 113 zeros in the standard units. An almost incomprehensibly vast amount of energy hidden in every scrap of nothing. Now here's the twist. We don't have to rely only on calculation, because we can actually measure the energy of empty space, indirectly, but genuinely, by watching what it does to the universe at large. And what it does is push. In 1998, two separate teams of astronomers were studying a particular kind of exploding star far out in the depths of the universe. These stars, called Type 1a supernovae, are precious to cosmologists because they explode with almost exactly the same intrinsic brightness every time, which makes them a kind of cosmic measuring stick. If you know how bright something truly is, and you measure how bright it appears from here, the difference tells you how far away it is. And by measuring how much the light of these supernovae had been stretched out on its long journey to us, the teams could work out how fast the universe had been expanding when each of those explosions occurred. They expected a particular answer. For decades, everyone had assumed that the expansion of the universe must be gradually slowing down. That seemed inevitable. The universe is full of matter, and matter has gravity, and gravity pulls things together. A universe full of gravitating stuff should be putting on the brakes, its expansion easing year by year, exactly as a ball thrown upward slows as Earth's gravity tugs it back. So both teams set out, essentially, to measure how quickly the cosmic expansion was decelerating. Instead, they found the opposite. The universe is not slowing down, it is speeding up. Its expansion has been accelerating, the galaxies rushing apart faster and faster as time goes on. Something is pushing outward against all that gravity and winning. Something with a kind of negative pressure, woven into the fabric of space itself. We now call it dark energy, and it is the great engine of the universe's fate. The two teams' discovery was so unexpected and so well confirmed that it would go on to win the Nobel Prize. And here is where the threads of our story tie themselves into a knot, because that mysterious dark energy driving the expansion has an energy density we can measure. From how fast the expansion is accelerating, we can work out how much energy is stored in each cubic meter of empty space. And the number we get is astonishingly, delicately small, roughly a decimal point, followed by 9 zeros, and then a small handful, a whisper of energy, almost nothing at all, in every cubic meter of vacuum. Now set the two numbers side by side. Quantum field theory calculates the energy of empty space and predicts a 1 followed by 113 zeros. The universe, measured directly, reports a whisper, a fantastically tiny number instead. The gap between the prediction and the measurement is around 120 orders of magnitude. That is a 1 followed by 120 zeros. It is, without any exaggeration whatsoever, the largest discrepancy between theory and observation in the entire history of science. Our best framework for the vacuum is not off by a factor of 2, or a million, or a trillion. It is off by a factor of 10 to the power of 120. Physicists call it the cosmological constant problem, and some, only half joking, call it the worst prediction in the history of physics. And what makes it so maddening is that the theory is clearly not simply wrong. We know vacuum fluctuations are real. The Casimir effect proves it, over and over, in the laboratory. We know energy comes in quantized packets and rides on the excitations of fields. All of that is confirmed, repeatedly, to extraordinary precision. And yet when we add up the total energy that all this well-verified physics implies should be sitting in empty space, we get an answer so catastrophically too large that if it were true, the universe would have torn itself apart in its first instant. Something, somewhere, is canceling almost all of it. Some unknown mechanism is quietly subtracting away that colossal predicted energy and leaving behind only the faint remnant we actually observe. And nobody knows what that mechanism is. There's a wonderful footnote here, one of history's great ironies. Back in 1917, Einstein himself had introduced a term into his equations of general relativity, a kind of built-in energy of space, in order to make the universe hold still, since at the time everyone believed the cosmos was static and eternal. He called it the cosmological constant. And when Edwin Hubble later discovered that the universe was in fact expanding, Einstein threw the term away in embarrassment, reportedly calling it the greatest blunder of his life. But the supernova measurements of 1998 brought it roaring back. The universe really does have a built-in energy of space, driving it apart. Einstein's blunder turned out to describe something real. He was wrong about being wrong. Physicists have proposed candidate escapes from the cosmological constant problem, but none has yet been confirmed. One of the most elegant is called supersymmetry, the idea that every known particle has a heavier partner of a complementary type. The appeal is beautiful. Particles of one type contribute to the vacuum energy with a positive sign, and their partners contribute with a negative sign, pushing in opposite directions. If supersymmetry were exact and perfect, the two would cancel precisely, and the vacuum energy would come out to exactly zero. The trouble is that the real vacuum energy isn't quite zero. It's tiny, but it's there, driving the acceleration. So if supersymmetry exists, it must be broken, with the partners having different masses from their counterparts, which would make the cancellation only partial. That could still help, but there's a deeper problem. We have searched for these partner particles at the most powerful atom smasher ever built and found nothing. Supersymmetry isn't ruled out entirely. The partners might simply be too heavy for our current machines to reach, but the simplest, most natural versions, the ones that would have helped the most, have been quietly eliminated by the evidence. Others have proposed some kind of self-adjusting mechanism, a field that dynamically settles the vacuum energy down toward a small value on its own. These ideas exist on paper. None of them has yet made a prediction that was then confirmed by observation. So the cosmological constant problem sits there still, unresolved, at the crossroads of quantum field theory, general relativity, and cosmology, resisting every attempt to solve it. And notice what kind of problem it is. It is a problem about the energy of empty space, about what energy is when it isn't attached to any matter at all, when it's just there, humming quietly in the fabric of space itself. We understand energy well enough to run the entire industrial and digital civilization on it, and we cannot correctly calculate how much of it is sitting in a cubic meter of nothing. That is the honest, humbling shape of what we know. So let's set that particular mystery to one side for a while. It will still be there when we come back, and approach the whole question of energy from a completely different direction. Because there's a piece of pure mathematics, proven just over a century ago, that gives the humble conservation of energy a meaning far deeper and more astonishing than anyone had ever imagined. And it was proven by a person who had to fight simply for the right to stand in a lecture hall and teach. Her name was Emmy Noether, and she was a German mathematician working at the University of Göttingen, one of the most gifted mathematical minds of her generation, by the estimation of the very people who defined that generation. And yet, because she was a woman, the German universities of her time refused her a proper position. For years, she worked without pay. For a while, her lectures had to be announced under the name of her colleague, David Hilbert, because the institution would not grant her the official right to teach under her own. Hilbert, to his lasting credit, was disgusted by this, and famously pointed out to the faculty that the University Senate was not a bathhouse. The objection to her sex was that absurd. Under those circumstances, treated as a guest in her own field, Emmy Noether proved what many physicists consider the most beautiful theorem in all of mathematical physics. Here is what she showed in 1915. Every continuous symmetry in the laws of nature corresponds, exactly and necessarily, to a conserved quantity. Wherever the laws of physics stay the same under some smooth change, something measurable must be conserved. Not might be, must be. The connection is not a coincidence or a pattern. It is a mathematical certainty, as unavoidable as the fact that a triangle's angles sum the way they do. That sounds abstract, so let's make it concrete, because the examples are stunning. Suppose the laws of physics are the same in every location, that an experiment performed in Tokyo obeys the same rules as the identical experiment performed in Toronto. That's a symmetry. Symmetry under moving from place to place. Noether's theorem says that this symmetry, all by itself, forces the conservation of momentum. Suppose the laws of physics don't care which direction you're facing, that nature has no preferred compass bearing, that symmetry forces the conservation of angular momentum, the steady spin of everything from a figure skater to a galaxy. And now the one we've been waiting for. Suppose the laws of physics are the same at every moment in time, that an experiment run today gives the same result as the identical experiment run tomorrow, or next year, or a billion years from now, that the rules themselves do not drift or age. This is called time translation symmetry, and Noether proved that this symmetry, this one fact about the world, forces the conservation of energy. Let that settle for a moment, because it quietly answers the question that has been hanging over this entire story since the 19th century. Remember the mystery we left with Joule and his paddle wheels? The universe seemed to be keeping perfect books on some quantity, and nobody knew why. Why should energy be conserved? Why should nature bother? Noether's answer: energy is conserved because the laws of physics do not change with time. That is the whole reason. Not because someone or something decided to conserve it, not because it merely happens to work out in experiments, because the mathematics demands it. If the laws are the same on Tuesday as they are on Wednesday, energy conservation follows as an ironclad consequence, and the logic runs in reverse too, which is where it gets haunting. If you ever witnessed a genuine violation of energy conservation, energy truly appearing from nowhere, or truly vanishing, it would mean something almost unthinkable, that the laws of physics themselves were shifting underneath you, that the universe had a preferred moment, that the rules of reality were not the same from one day to the next. Every time energy balances, in a chemistry experiment, in a car engine, in the collision of two galaxies, the universe is quietly certifying that its laws are steady across time. Noether's theorem is not nearly as famous outside physics as it deserves to be. It belongs alongside the greatest results in the history of science because it changed what conservation laws are. Before her, they were observed regularities, impressively reliable patterns in the data. After her, they were understood as direct consequences of the symmetries of nature. Momentum is conserved because space has no special place. Angular momentum is conserved because space has no special direction. Energy is conserved because time has no special moment. And this gives us, at last, a genuinely deep answer to what energy is. Energy is the conserved quantity that arises because physics is symmetric in time. It is, in a precise and meaningful sense, the thing that stays the same while time changes everything else. You cannot have energy, not this energy, not the conserved bookkeeping quantity of physics, without time. The two are bound together, inseparable, two faces of a single underlying structure. Energy is what a physical system holds steady as time flows through it. Keep that thought close, because everything that follows will keep circling back to it. Energy and time, locked together. It's a partnership we're going to see again in the quantum world, in the expanding universe, and at the very edge of what physics can currently say. But before we go further down, we need to pause on something that happened between Planck's packets and the full machinery of quantum fields. Something that changed what energy was attached to and then dissolved the boundary between energy and space itself. In 1905, the same miracle year in which he explained the photoelectric effect, Einstein published special relativity. And 10 years later, in 1915, he completed the general theory of relativity. Between them, these two theories rewrote the place of energy in the universe in ways that even now are not fully absorbed into the way most of us picture the world. Special relativity revealed, first of all, that energy and momentum are not two separate things. They are components of a single, unified object, partners in a four-dimensional package, 1 part energy and 3 parts momentum, welded together the same way relativity welds time to space. And just as two observers moving differently will disagree about distances and durations, they will also disagree about how much energy a given particle has and how much momentum. Neither observer is wrong. Energy, it turns out, is partly in the eye of the beholder. It depends on your own state of motion. What the observers will always agree on is a particular combination of the two, a kind of invariant core. And that invariant core is what we call the rest mass of the particle. Mass is what's left of energy and momentum when you strip away everything that depends on the observer. It's the part of the story everyone agrees on. And for a photon, that invariant core is exactly 0. A photon has no rest mass at all, which is why it can never rest, why it moves at the speed of light for every observer, always, and why it appears to us as something like pure energy in flight, pure momentum, with nothing held in reserve. General relativity then went much further and did something that still feels audacious a century later. Einstein showed that energy, all energy, in every form, not just the energy locked up in matter, curves space and time. A box filled with nothing but light curves the space-time around it. A powerful electromagnetic field curves space-time, and most remarkably of all, the energy of the gravitational field itself curves space-time, which means gravity gravitates. Gravity feeds on itself. This self-referential loop is what makes the mathematics of general relativity so ferociously difficult compared to other theories. The source of the curvature includes the curvature's own energy, the equation eating its own tail. But for our story, general relativity carries a subtler and stranger consequence, one that most people have never heard. In an expanding universe, the conservation of energy, the sacred law we've been building up all this time, becomes genuinely complicated. Here's the puzzle in its sharpest form. As the universe expands, space itself stretches, and light, traveling through that stretching space, gets stretched along with it. Its wavelength grows longer, its frequency drops, and since a photon's energy is Planck's constant times its frequency, each photon loses energy as it travels. The ancient light from the early universe has been stretched so much on its 14 billion year journey that it has faded from a blinding glare into a faint microwave hum. So ask the obvious question, where did all that energy go? And the unsettling answer is, nowhere obvious. It doesn't turn into heat somewhere. It doesn't get deposited into some other account. It just diminishes. The resolution takes us straight back to Emmy Noether. Her theorem says energy conservation follows from the laws of physics being the same at all times. But an expanding universe is not the same at all times. Its very geometry is changing. Space itself is different today than it was yesterday. The symmetry that guarantees energy conservation is, on the largest scales, simply not there. And so the guarantee lapses. In any small region of space-time, small enough that the cosmic expansion doesn't matter, energy is still perfectly conserved, locally, just as we always learned. Nothing appears or vanishes at a point. But if you try to add up the total energy of the whole expanding universe and demand that it stay fixed over time, you find the question itself has gone soft. The answer depends on how you slice things, on choices with no unique right answer, in ways that have no parallel in everyday physics. Cosmologists themselves handle this in different ways. Some will tell you plainly that energy is not conserved in an expanding universe. Others say it is conserved, but only if you carefully include the energy of the gravitational field itself in the ledger. Still others say the question of global energy conservation in general relativity is simply not well posed, that it's a question the theory declines to answer. All three positions are defensible, and the fact that experts can hold all three is itself the lesson. Energy is not as simple and not as universal as it first appears. It is a concept that works flawlessly in the small, in laboratories, in engines, in atoms, and grows subtle and slippery at the scale of the whole cosmos, where the geometry of space-time itself is in motion. And this, in turn, is one more reason physicists so badly want a theory of quantum gravity, a framework uniting quantum mechanics with general relativity. Such a theory would tell us what energy means when space and time themselves are quantum objects, whether conservation of energy holds in some deep fundamental sense, or whether it's an approximate feature that emerges only in the calm, flat regions of the universe where we happen to live. We don't have that theory yet. Hold on to that open door. We'll walk up to its threshold before the end. There's another thread in this story, one that has grown steadily more important in modern physics, and it connects energy to something you might never have expected: information. The thread begins, fittingly, with a demon. In the 19th century, James Clerk Maxwell, the same Maxwell whose equations described light, dreamed up a mischievous thought experiment. Imagine a container of gas divided into two chambers with a tiny door between them, and imagine a minuscule demon stationed at that door, watching the gas molecules as they zip around. The molecules are a mixture of fast ones and slow ones. Whenever a fast molecule approaches the door from the left, the demon opens it and lets it through to the right. Whenever a slow one approaches from the right, the demon lets it pass to the left. The demon does no pushing, no pulling. It merely opens and closes a door at the right moments. And yet, over time, the fast molecules accumulate on one side and the slow ones on the other. One chamber grows hot, the other grows cold, and a temperature difference is a usable resource. You can run an engine off it. The demon appears to have created useful energy out of nothing but careful sorting. The problem is that this flatly violates one of the most trusted principles in science, the second law of thermodynamics. The second law says that in a closed system, disorder, measured by a quantity called entropy, always increases. Heat does not spontaneously separate itself into hot and cold. Order does not arise for free. Cream stirred into coffee does not unstir. And yet Maxwell's demon, armed with nothing but a door and good eyesight, seemed to make order out of chaos without paying for it. For decades, this little paradox nagged at physicists. Where was the catch? The answer finally came in 1961 from a physicist named Rolf Landauer working at IBM, and it is one of the most quietly profound insights of the 20th century. Landauer noticed what everyone else had overlooked. The demon has to remember things. To decide whether to open the door, it must observe each molecule, fast or slow, and record the result. if only for an instant, and its memory is not infinite. Sooner or later, to make room for the next observation, the demon must erase an old one. And here is Landauer's revelation. Erasing information has an unavoidable energy cost. Deleting even a single bit of information, one yes or no, one fast or slow, necessarily releases a tiny, precisely calculable minimum amount of heat into the surroundings, an amount set by the temperature and by Boltzmann's constant. That tiny toll is what saves the second law. The demon isn't getting something for nothing after all. It's paying, not in the muscle work of opening the door, but in the bookkeeping. Every bit it wipes from its memory bleeds a little heat into the world, and when you tally it all up, the books balance. Entropy wins, as it always does. For half a century, this remained a theoretical argument, elegant but untested. Then, in 2012, researchers actually did it. Working with a single microscopic particle used as a one-bit memory, teams in Lyon and Stuttgart erased individual bits of information and measured the whisper of heat released each time. It matched Landauer's prediction. Information, it turns out, is physical. It is not an abstraction floating above the world. It is embodied. It takes up residence in matter, and destroying it costs energy, always, everywhere, as a matter of physical law. This means energy and information are joined at a level far deeper than metaphor. The entropy of a system, it turns out, is really a count of information, a measure of how many microscopic arrangements are consistent with what you can see from the outside. And the exchange rate between information and energy is set by temperature. The second law of thermodynamics, seen through this lens, is really a statement about knowledge. The universe tends, relentlessly, towards states about which we know less and less at the microscopic level. And this thread, energy woven together with information, runs all the way to the strangest objects in the cosmos. In 1974, Stephen Hawking showed that black holes are not perfectly black. Near the event horizon, the boundary of no return, the restless quantum vacuum we met earlier, does something remarkable. Fluctuations there give rise to pairs of particles, and it can happen that one member of the pair falls into the black hole while the other escapes to infinity. To a distant observer, the black hole appears to glow, faintly, with thermal radiation, and in doing so it slowly loses energy. It evaporates. The smaller the black hole, the hotter it glows, and the faster it shrinks. In one stroke, Hawking had tied together quantum mechanics, gravity, and thermodynamics. Because if a black hole has a temperature, it must have an entropy, an information content. And a young physicist named Jacob Bekenstein had already worked out, in 1972, what that entropy must be. The answer is one of the most suggestive results in all of physics. The entropy of a black hole is proportional not to its volume, but to the surface area of its horizon. As if all the information about everything that ever fell in were recorded not throughout its interior, but written on its two-dimensional boundary, roughly 1 bit for every tiny patch of horizon a few Planck lengths across. This idea has a name, the holographic principle. The suspicion, and among many theorists it is now considerably more than a suspicion, that the information content of any region of space is fundamentally encoded on its boundary, the way a hologram stores a three-dimensional image on a flat film. If that principle is truly general, its implications for our question are enormous. If information is physical, if erasing it costs energy, if the information in a volume of space lives on its surface, then energy and information are not two subjects that happen to touch. They are entangled at the root. Energy may be, among everything else it is, the currency in which the universe's information is stored, moved, and paid for. The full implications are still being worked out, on blackboards and in journals, right now. But it seems increasingly likely that any final answer to what is energy made of will have the word information somewhere inside it. Let's come back down to Earth now, all the way down to something you may have sitting in a drawer. Because there's a device, cheap enough to clip onto a keychain, that is a direct, everyday window into everything we've discussed about quantized energy: a laser. A laser produces light of a very particular character. Every photon in the beam is in the same quantum state, the same frequency, the same phase, marching in step, the same direction, the same polarization. Physicists call this coherent light, and it is utterly unlike the light of a candle or the sun, which is a jumble of frequencies and phases tumbling out in all directions. The name itself is an acronym: light amplification by stimulated emission of radiation, and the key phrase in it, stimulated emission, was predicted by Einstein, once again, all the way back in 1917, decades before anyone built one. Here's how it works, and notice how everything we've learned comes together. Take an atom and lift one of its electrons to a higher rung on its energy ladder, an excited state. Left alone, the electron will eventually drop back down on its own, releasing a photon with exactly the energy of the gap. But Einstein realized something subtle. If a photon of exactly that gap energy happens to pass by the excited atom first, it can trigger the atom to release its energy early. And here is the magic. The new photon that emerges is a perfect twin of the one that triggered it. Same frequency, same phase, same direction. Where one photon passed, two now travel in perfect lockstep. Now let those two photons fly onward through a material full of other excited atoms. Each one can trigger another emission. 2 become 4, 4 become 8, 8 becomes 16. The light amplifies itself in an exponential cascade of identical photons, a chorus growing louder, with every voice singing the same note in the same breath. That is the amplification in the acronym. There's a catch, of course. This only works if more atoms are sitting in the excited state than in the ground state, a condition called population inversion, which is thoroughly unnatural. Normally, atoms overwhelmingly prefer the ground floor. So to build a laser, you must pump energy in, with electrical current or with another light source, pushing atoms up the ladder faster than they can fall back down. That pumped-in energy is what eventually streams out as the beam. The entire operation, from the wall socket to the spot of red light on the far wall, is one long cascade of quantized energy transitions. Energy in, electrons lifted to precise rungs, photons of one exact energy, triggering more photons of that same exact energy, coherent light out. The narrow purity of a laser's color is a direct portrait of the sharpness of atomic energy levels, which is a direct consequence of quantization, which is a direct consequence of the wave nature of matter, which is quantum mechanics itself. From Planck's uncomfortable fix in the year 1900 to the laser pointer in your drawer, one unbroken century of physics, connected end to end. And there's another phenomenon, stranger still and closer to science fiction than almost anything else in a laboratory, that makes the quantum nature of energy impossible to dismiss. It's called superconductivity. Take certain materials and cool them below a critical temperature, and something happens that classical physics says cannot happen. Their electrical resistance drops to zero. Not very low, not almost nothing, exactly zero. An electric current started in a loop of superconducting wire will circulate forever, with no battery, no power source, no losses of any kind. This is not a theoretical claim. A current set flowing in a superconducting ring in the early 1960s is, as far as anyone can measure, still flowing today, more than 60 years later, undiminished, a river that never runs down. Classically, this is flatly impossible. In an ordinary wire, electrons streaming along are constantly jostled by the vibrating atoms of the metal around them, losing little bits of energy as heat with every collision. That's what resistance is, friction for electricity. You can make it small, but you can never make it vanish. There will always be jostling, always be losses. Except, below that critical temperature, there aren't. Something changes the rules. What changes them is quantum mechanics, operating not on one particle, but on trillions at once. At low enough temperatures, the electrons in these materials do something deeply counterintuitive. They pair up. Two electrons, which repel each other fiercely under normal circumstances, since both carry negative charge, become bound together into a partnership called a Cooper pair. Their matchmaking mediated, delicately, by vibrations in the crystal lattice of the metal itself, and these pairs have a collective character that single electrons lack. Single electrons are loners by law. A rule called the exclusion principle forbids any two of them from occupying the same quantum state, which is, incidentally, the reason atoms have structure at all, and the reason you don't fall through the floor. But paired electrons play by different rules. Pairs are permitted, even inclined, to crowd together into one shared state. And below the critical temperature, that is exactly what they all do. Every Cooper pair in the material condenses into a single, unified quantum state, one wave function, describing the entire piece of metal, trillions upon trillions of electrons, all moving as one coordinated whole. Think of the difference between a crowd of pedestrians and a marching band. In the crowd, everyone dodges and bumps and stumbles, losing energy in every collision. In the band, every member moves in perfect formation, and there are no collisions because there is no independent motion left to collide with. When current flows in a superconductor, that whole unified state glides together. For a single electron to scatter off an atom and lose energy, it would have to break out of the formation, shatter its pair, and tear itself away from the collective, and that costs more energy than exists in the cold, quiet material. So nothing scatters, nothing is lost. The current flows without resistance, protected by an energy gap, a discrete, quantized cost of disruption. It is, once again, the graininess of energy, the existence of a gap with nothing in it, that makes the miracle possible. And this particular miracle is quietly running through your world. The MRI machine at a hospital wraps its patient in a magnetic field generated by superconducting coils. The great particle accelerators steer their beams with superconducting magnets, and the quantum computers now being developed in laboratories around the world use tiny superconducting circuits as their fundamental elements, circuits whose discrete, quantized energy levels serve as the bits of an entirely new kind of computation. Follow that lineage back, and you arrive, once more, at Max Planck in 1900, reluctantly proposing packets of energy to fix a formula about glowing objects. His unwelcome idea has become the foundation of the most sophisticated technology human beings have ever attempted to build. Now let's go the other way, not down into cold, quiet materials, but up into the most violent energies humanity can create. Because there is a place where the equivalence of energy and matter is put on display billions of times a second in the most direct way imaginable. Beneath the countryside on the border of France and Switzerland runs a circular tunnel 27 kilometers around, and inside it, the Large Hadron Collider accelerates protons to within a whisker of the speed of light. Two beams race in opposite directions and are steered into head-on collisions at energies more than 10,000 times greater than the energy locked in a proton's own mass. At those energies, the protons do not survive. They are torn open, their inner constituents, quarks and gluons, colliding directly. And out of the sheer energy of the impact, new particles are born, pairs of quarks and antiquarks, heavy, short-lived particles that existed in abundance only in the universe's first instance. And, in collisions recorded in 2012, the long-sought Higgs boson itself. Watch what is actually happening there, in the language we've built. Pure energy of motion goes in, new matter comes out. This is Einstein's famous equation, not as a formula on a t-shirt, but as an event. Energy crystallizing into mass before the eyes of the detectors. In the picture of quantum field theory, the collision energy pours into the quantum fields and sets them ringing, and those ringings are particles. New particles with real masses, conjured from kinetic energy, living for fleeting fractions of a second before decaying into lighter things that spray outward into the surrounding instruments. From the tracks they leave, physicists reconstruct each event, every one of them a snapshot of the universe's bookkeeping in action. And here is the quiet, remarkable verdict of that colossal machine. Over more than a decade of operation, across billions upon billions of recorded collisions, in an ocean of data measured in petabytes, there has not been one single event, not one, in which the energy coming out failed to match the energy going in. Not one violation of conservation, not one exception to the quantum rules. Down to the smallest distances ever probed, scales 10,000 times smaller than a proton, the same laws hold, the same ledger balances, the same symmetry that Emmy Noether identified keeps its promise without fail. Since the Higgs has entered our story, let's give it its proper place, because it completes the picture of what mass, and therefore a great deal of the energy in your body, actually is. The Higgs field, like all the fields of quantum field theory, fills the entirety of space. But it's unusual. Unlike the others, it doesn't sit at zero in empty space. It has a constant, non-zero value everywhere, a kind of ever-present medium pervading the universe. And every kind of particle interacts with this medium to a different degree. Here's a rough picture. Imagine wading through water. Some things, a fish, streamlined and slick, slip through almost effortlessly. Other things, say, a person walking chest deep, feel the medium dragging on every attempt to speed up or slow down. The Higgs field is something like that universal medium and a particle's resistance to being accelerated, which is precisely what we mean by its mass, is set by how strongly it couples to the field. The neutrino barely notices the Higgs field and is almost massless. The top quark grips it ferociously and is the heaviest fundamental particle known, nearly 200 times the mass of a proton, and the photon does not couple to the Higgs field at all, which is exactly why it is massless, why it always travels at the speed of light, and why it can never, under any circumstances, be brought to rest. The Higgs boson, discovered in 2012, after decades of searching and the construction of the largest machine in human history, was the ripple in that field, the excitation that proved the medium is really there. And with it, the final piece clicks into place. Mass is not a substance either. Mass is a form of energy, the energy cost of an excitation in a field, set by that field's coupling to the Higgs. The famous equation, energy equals mass times the speed of light squared, is not saying that mass can be converted into energy, as if they were two different substances with an exchange rate. It is saying something far more radical. They were never two things. Mass is energy, wearing a different name, energy at rest, energy bound up in the very existence of a particle. The speed of light squared is just the conversion between the units humans happened to invent, for each before we realized they were the same. Nuclear physics made this undeniable, visibly, measurably, and in one terrible application, unforgettably. When a heavy uranium nucleus is struck by a neutron and splits into two smaller nuclei, careful accounting reveals something eerie. The fragments, added together, weigh slightly less than what you started with, only about 0.1% less. But multiply that missing sliver of mass by the speed of light squared, an enormous number, 90 quadrillion in standard units, and you get a staggering release of energy. That is the arithmetic inside a reactor and inside a bomb. But here is what's almost always misunderstood about it, and it matters for everything we've been building. The mass did not convert into energy, as though one substance transformed into another. The mass was energy all along. What actually happened is that energy stored in the binding of the uranium nucleus, the grip of the strong nuclear force holding its protons and neutrons together, was released when the pieces rearranged into more tightly bound configurations. That binding energy had been contributing to the nucleus's mass, because all energy has mass, because they are the same thing. When the arrangement changed, the stored energy became energy of motion, the fragments flying apart at tremendous speed, and the total, as always, balanced exactly. Nothing was created. Nothing was destroyed. Noether's ledger, enforced by the steady sameness of time, held perfectly, as it apparently always has, and apparently always will. We are getting close now to the bottom, to the deepest, most honest description physics can currently give of what energy is. And I should warn you gently, at this depth, energy stops looking like anything at all. It has no color, no texture, no shape. It is not a glowing fluid, not a substance you could bottle. What it is, at the level of our most precise theories, is a relationship between the state of the world and the flow of time. Let me show you what that means. At the heart of quantum mechanics sits a mathematical object called the Hamiltonian, named for the 19th century Irish mathematician William Rowan Hamilton, who reformulated the mechanics of his day in a form so elegant that, a century later, it turned out to be tailor-made for the quantum revolution he never lived to see. In classical physics, the Hamiltonian is simply a number, the total energy of a system, kinetic plus potential. But in quantum mechanics, it becomes something richer, an operator, a mathematical instruction, a machine that acts on the wave function and extracts information from it. And here is its true role, the one that ties our whole story together. The Hamiltonian is the generator of time evolution. The Schrödinger equation, the master equation of the quantum world, says, in essence, one thing: the way a system's wave function changes from this moment to the next is given by the Hamiltonian acting upon it. The Hamiltonian is the engine of becoming. It is the mathematical embodiment of the ticking of time for a quantum system. Everything flows from it: the dynamics, the allowed energy rungs, the possible transitions, the response to every push and pull. And the allowed energies of a system? They are the specific values the Hamiltonian can return, the characteristic numbers of that operator, its spectrum. When you measure a system's energy, one of those numbers is what you get. So at its mathematical bedrock, energy is a spectrum of numbers, the values yielded by the very operator that drives a system forward through time. This is not a poetic flourish. It is the working definition in every quantum mechanics textbook on Earth. Energy is what the Hamiltonian measures, and the Hamiltonian is what makes time happen. Energy is what you find when you ask how a quantum system responds to the passage of time. Do you hear the echo? This is Emmy Noether's insight, returned in quantum dress. Energy and time are two sides of one structure. She proved it through symmetry. The Hamiltonian embodies it through dynamics. Two different roads, arriving at the same quiet truth. And quantum mechanics seals the partnership with one more remarkable feature. Energy and time obey an uncertainty relation of their own, a sibling of the famous one between position and momentum. The more precisely a system's energy is defined, the more time is required for it to be so. A stable atomic ground state, which endures forever, has all the time in the world, and so its energy is perfectly, infinitely sharp. But an excited state that survives only briefly before decaying is a different story. Its short life means its energy is genuinely blurred, spread across a small range, not because anyone measured clumsily, but because the state itself does not possess a single sharp energy. And this blur is visible. The spectral lines from short-lived states are measurably broader than those from long-lived ones. A state that exists for only a millionth of a billionth of a second simply does not have a well-defined energy in the classical sense. Its energy is smeared in proportion to the brevity of its existence. Think about what that is saying. Energy, at this level, is not a property a thing simply has, the way a stone has a weight. Energy requires time in order to exist as a sharp, definite quantity. A thing must persist in order to have a precise energy. The fleeting is fundamentally blurry. Energy is, in the deepest sense we know, the shadow that time casts on the physical world. And the scale of the whole relationship, the exchange rate between duration and definiteness, is set, once again, by Planck's constant. That same tiny number, everywhere, always. So here is where we stand. Energy is quantized, and we know why. Energy is the excitation of fields that fill all space, and particles are what those excitations are called. Empty space itself hums with energy we can measure, but cannot correctly calculate. Mass is energy at rest. Conservation of energy is the fingerprint of time's steady sameness. And energy itself, at bedrock, is the spectrum of the operator that generates time. It is a magnificent structure, and yet, even accepting every word of it, the question does not fully close. Because the fields themselves still have to come from somewhere. And here, honesty requires us to walk right up to the edge of what anyone knows. Why do the fields have the properties they have? Why does Planck's constant have the value it does? Why does the electron couple to the Higgs field with precisely the strength it does, giving it precisely the mass that, as it happens, allows atoms to be the size they are, chemistry to work the way it does, and you to exist? Why are there 3 dimensions of space and not 2, or 4, or 17? Why does time run forward? Quantum field theory is, by any measure, the most precisely tested framework in the history of human thought. There is a property of the electron, the strength of its interaction with a magnetic field, which the theory predicts and experiment measures, and the two agree to better than 1 part in a trillion. That is like measuring the distance from the Earth to the Moon and being correct to within the width of a single human hair. No other scientific theory has ever come close. And yet this same magnificent theory does not explain where its fields came from, or why they carry the particular properties they do. The standard model of particle physics contains roughly 19 free parameters, numbers like the masses of the quarks, the strengths of the couplings, the value of the Higgs field in empty space, that cannot be derived from anything deeper. They are measured in experiments and typed in by hand. The theory accepts them, works flawlessly with them, and is silent about why those values and not others. They are simply there, encoded in the fields, expressed as energy scales, unexplained. The most ambitious attempt to explain them has been string theory. The proposal, which emerged in the 1970s and grew into a vast research program, is that the fundamental entities of nature are not point particles at all, but tiny one-dimensional strings, filaments of something, vibrating. And just as a single violin string can sound many different notes depending on how it vibrates, a single kind of fundamental string could manifest as many different particles depending on its mode of vibration. One vibration is a photon, another is an electron, another is a quark, In this picture, all the particles of nature are unified into one kind of object, and energy, the theme of our whole journey, becomes, quite literally, the vibrational energy of strings. All matter, a music. String theory has genuine achievements. Most strikingly, it naturally contains gravity. The graviton, the hypothetical carrier of gravitational force, appears automatically among the vibration modes, unbidden, something quantum field theory had struggled with for decades. But the theory also demands a steep price, extra dimensions of space beyond the 3 we experience, usually 6 or 7 more, curled up so small that we cannot perceive them, and the properties of the particles we observe would depend on the precise shape into which those hidden dimensions are folded. The trouble is that the number of possible shapes is estimated at perhaps 10 to the power of 500, each one corresponding to a different universe with different physics. And decades of extraordinary mathematical development have not yet produced a single testable prediction confirmed by experiment. This is not necessarily because string theory is wrong. It's because the strings, if they exist, would vibrate at a scale some 20 orders of magnitude smaller than anything our instruments can reach. No accelerator we can currently imagine building could probe it. String theory remains a beautiful hypothesis, perhaps true, perhaps not, suspended, for now, beyond the reach of judgment. A rival approach, called loop quantum gravity, starts from the opposite shore. Rather than beginning with quantum theory and hoping gravity emerges, it takes Einstein's central lesson, that gravity is the geometry of space-time itself, and asks, what happens if you quantize the geometry? What if space itself is subject to the graininess we've found in everything else? The answer the theory gives is striking. Space, at the unimaginably tiny Planck scale, is not a smooth continuum. It is granular, woven from discrete units, a network of elementary chunks of geometry with a smallest possible area and a smallest possible volume, below which the words space and time simply cease to apply. The smooth, continuous world we experience would emerge from this underlying granularity, the way the smooth surface of water emerges from discrete molecules, an illusion of continuity, born of scale. In such a picture, energy as we know it, a quantity defined against the steady flow of time, would itself be an emergent thing, arising only when the deep quantum foam of geometry averages out into something resembling smooth spacetime. Some versions of loop quantum gravity even suggest that the Big Bang was not a beginning, but a bounce, a previous universe contracting to unimaginable density and rebounding into the expansion we now inhabit. These are testable ideas in principle, with possible faint signatures in the oldest light of the universe, but nothing has yet been confirmed. And loop quantum gravity and string theory remain incompatible visions. They cannot both be right as they stand. We do not know which, if either, describes reality at the bottom. So the deepest version of our question, what is energy when space and time are themselves quantum, currently has no answer. Not because physicists haven't thought hard, but because the answer lives at scales our finest instruments cannot touch. Energy is defined through time. Time, in general relativity, is part of the geometry of space-time, and that geometry, at the Planck scale, becomes a fluctuating, indefinite, quantum thing. In a quantum space-time, what does it mean for time to flow? And if time does not flow definitely, what does conservation of energy even mean? These are questions without answers, but they are the right questions, the ones any final theory of physics will have to face. While we wait at that frontier, there is one more humbling accounting to face, a census of the universe itself, because the standard model, for all its trillion-fold precision, describes astonishingly little of what's actually out there. When cosmologists tally the total energy content of the universe, the ordinary matter, every star, every planet, every cloud of gas, every atom of every kind that our beautiful theories describe so precisely, comes to only about 5% of the whole. Around 27% is something called dark matter, an unseen substance that clusters around galaxies, bending light, holding spinning galaxies together when their visible mass alone could not, shaping the growth of cosmic structure since the earliest times. We can map where it is with confidence. We have not the slightest confirmed idea what it is. Every experiment built to catch a dark matter particle has, so far, caught nothing, and the remaining 68% is the dark energy we met earlier, the energy of empty space driving the accelerating expansion, whose measured value defies our best calculation by those infamous 120 orders of magnitude. Its effects we know precisely, its nature not at all. Sit with that ratio for a moment. Our finest theory in history accounts, exquisitely, for 5% of the universe. For the other 95%, we have two names: dark matter, dark energy, and names, in science, are sometimes just carefully labeled ignorance. It's entirely possible that when those mysteries are finally solved, both will turn out to be forms of energy we simply haven't yet learned how to recognize. The story of energy, in other words, is not a finished chapter of science. It is most of the unwritten book. But rather than end out there, in the dark, let's bring everything home, all of it, every idea we've gathered tonight, through the biography of a single particle, a photon, because the full arc of what energy is can be told in the journey of one quantum of light, from its birth in an atom to the moment it becomes part of you. Somewhere, an electron sits on an upper rung of an atom's energy ladder. It drops to a lower rung. The energy difference between those two rungs, exact, discrete, non-negotiable, leaves the atom as a photon, a single quantum of the electromagnetic field, carrying precisely Planck's constant times its frequency. Not roughly, precisely. That photon crosses the space between the atom and your eye, and as it travels, it is not a little glowing ball tracing a line through the dark. It is a ripple in a field that fills the universe, an excitation spread out as a wave of probability, in a real sense exploring every available path at once, its possibilities overlapping and interfering like ripples on a pond. It is the energy it carries. The two cannot be separated even in principle. And then it reaches you. It plunges into your eye and is absorbed by a single molecule called retinal, cradled inside a protein, inside a photoreceptor cell at the back of your retina. In that instant of absorption, the photon ceases to exist, and its energy, the entire packet, all at once, all or nothing, lifts an electron in that molecule to a higher rung. The molecule, jolted, snaps into a new shape. That shape change trips a cascade of chemical reactions. The cascade opens tiny channels in the cell's membrane. Charged atoms flow. A voltage shifts. A nerve fires. A signal races along the optic nerve into the visual cortex of your brain, and you see. Every single step in that chain, from the atom's glow to your experience of light, is a discrete, quantized energy transaction. An electron falls one exact interval. A photon is born with one exact energy. That energy is delivered whole, or not at all. A molecule accepts it and changes. Charges move in countable numbers. Nowhere in the entire chain is there a single, smooth, continuous, classical transfer. The universe conducts all of its business, including the business of you seeing the world, in exact quanta. Vision itself is built from billions of these little completed transactions every second. a ceaseless quantum commerce between the world and your mind that you experience simply as looking. And so, at last, we can face the question we set out with and answer it as honestly as physics allows. What is energy made of? The truthful answer is, energy is not made of anything, not in the way that water is made of molecules, or molecules of atoms, or atoms of smaller particles still. Every other time science has asked, what is this made of, there was a smaller ingredient waiting underneath. Energy is where that chain of questions stops. It does not reduce. There is no grain of energy stuff to find, because energy was never a stuff at all. What energy is, as far as the deepest reach of current physics can tell, is a structure, a single structure seen from many angles, and every angle we've visited tonight is one of its faces. From the angle of symmetry, energy is the quantity that must be conserved because the laws of nature do not change with time, Emmy Noether's immortal insight. From the angle of the quantum, energy is the spectrum of the Hamiltonian, the numbers yielded by the very operator that generates the flow of time. From the angle of the fields, energy is what an excitation carries, indeed, what an excitation is, and every particle in existence is such an excitation, which means energy is not something matter has, but something matter is. From the angle of the vacuum, energy is the irreducible hum of empty space, real enough to pull metal plates together, mysterious enough to defy our calculations by 120 orders of magnitude. From the angle of the cosmos, it is the currency of creation itself, crystallizing into new particles wherever enough of it gathers. And from the angle of an ordinary evening, it is the candle burning, the meal becoming warmth, the light arriving at your eye. These are not different things. They are one thing, described at different scales, and the consistency between them never breaks. The same quantization that sharpens the spectral lines of hydrogen makes lasers pure and superconductors perfect. The same conservation that balances a chemical reaction balances the collision of galaxies. The rules hold in your kitchen, and they hold 12 billion light-years away, without exception, without fatigue, without a single confirmed violation in the entire recorded history of measurement. There is no negotiating with it, and there are no special cases. Not because some authority stands guard over the rule, but because the laws of nature are the same at every moment, and that sameness, Noether showed us, is what energy fundamentally is. Which leads to the last, quiet thought, perhaps the deepest one in all of physics. It may be that symmetry itself is the most fundamental thing there is, more fundamental than particles, which are only ripples, more fundamental than the fields, whose forms the symmetries constrain. The particles, the forces, the structures of the universe, all of them may be expressions of symmetry. The symmetry comes first. Everything else follows. So consider, one more time, where you are right now. In the air you just breathed in, electrons are resting on precisely quantized rungs, refusing, as they have for billions of years, to occupy any energy in between, and that refusal is the only reason atoms exist, the only reason chemistry repeats itself faithfully enough to build and rebuild a living body, the only reason there is a you to consider anything at all. Photons are shuttling between the molecules around you, each one carrying its exact package. The vacuum in the small spaces between things is quietly humming in every cubic centimeter with the ground state energy of fields that fill the universe. And through all of it, at every scale, one rule holds. Something is staying constant while time changes everything else. You began tonight with a word you'd heard 1,000 times. Energy, the thing on the bill, the thing in the battery, the thing you feel short of on a long afternoon. And now you know what it really is. Or rather, you know the shape of the honest answer. It is not one of the things inside the universe. It is part of the architecture of the universe, the rule book written into existence itself. The one thing that holds steady so that everything else can change. Every time you switch on a light, every time your heart beats, every time a distant star fuses hydrogen in its silent core, the same mathematical symmetry, the same steady sameness of time itself, is being honored exactly, everywhere, without exception. The next time you watch a candle burn down or feel the sun's warmth arrive across 93 million miles of vacuum onto the back of your hand, take a moment to notice what you're really witnessing. Not a substance being used up, a structure being obeyed, the oldest law there is, keeping its books in perfect balance, as it has since the first instant of time, and as, quietly, it always will.